You look at a robotic dog executing, like a flawless backflip or an autonomous vehicle threading its way through this chaotic intersection, right? And your brain immediately maps a narrative onto it.
Oh, absolutely. We can't help it.
Right. You see a machine that has this kind of localized genius,
Yeah.
a brain directing muscles. But, and this is what we're getting into today, you lift the hood, strip away that sleek plastic chassis, and that illusion just completely shatters.
Yeah, you aren't looking at a synthetic brain at all.
No. You're staring at this flat, layered slab of fiberglass, a printed circuit board, and it's peppered with these minuscule, completely inanimate blocks of silicon, ceramic, metal.
It really creates this profound cognitive dissonance. I mean, we're so conditioned to view software as this weightless, ethereal logic,
You're just floating in the cloud somewhere.
Exactly. But code doesn't exist in a vacuum. It is utterly bound by the physical medium it runs on, the intelligence of that robotic dog. It's entirely contingent on, like, the thermodynamics of a single copper trace or the electrostatic fields inside a microscopic sliver of silicon.
Which is the core of our deep dive today. We've got this massive stack of source material. We're talking Texas Instruments, motor drive architectures, STM32 high-speed layout guidelines, dense mechatronic handbooks, and even U.S. LiDAR integration notes.
Some heavy reading.
Very heavy. But our mission is to look past the code. We are diving into the raw physics of how lifeless material is orchestrated to, sense, think, and exert massive physical force. And we are doing this without leaning on those basic high school analogies.
Right, no water flowing through pipes today.
Exactly. If you're managing complex robotic systems, you already know what a resistor and a capacitor are. So our goal is to uncover the extreme edge cases, the parasitic physics that emerge when you push these components to their absolute limits.
Because the components you model in a perfect software simulation, they behave wildly differently when you actually solder them onto a board that's subjected to extreme heat, vibration, high-frequency switching. I mean, a resistor is never just a resistor at 2 gigahertz.
Okay, let's unpack this. Let's start right there with the passive components, the foundational stuff that doesn't inject power, but manipulates the electromagnetic fields.
Right.
Now, in basic applications, you throw a resistor in to limit current. Simple enough.
Yeah.
But in the TI motor control documents, resistors are elevated from just, current limiters to highly sensitive environmental sensors.
Oh, yeah. They use something called shunt resistors to determine exactly how much torque a heavy robotic arm is applying.
Which is wild, because torque control is everything, right? If you over-torque, you crush the object. If you under-torque, you drop it.
Exactly. And sure, you could use a complex mechanical torque sensor, but those are heavy. They're expensive. The mechatronic approach is to just measure the current flowing into the motor phases.
Because current equals torque in those motors.
Right. In a permanent magnet synchronous motor, current is directly proportional to torque. So we place a shunt resistor right in series with the motor phase.
But wait, if you have a robotic arm lifting a huge payload, that motor might be pulling, 50 amps?
I believe 50 amp.
So if you put a resistor in the path of 50 amps, aren't you going to generate a catastrophic amount of heat? I mean, you're essentially building a tiny space heater on your logic board.
That is exactly the engineering hurdle. To survive that without instantly vaporizing, a shunt resistor has to have an incredibly low resistance. We're talking milliamps or even microoms.
Wow.
Yeah, it's usually this specialized, thick piece of manganese copper alloy. So when 50 amps flow through a 1 milliohm shunt, it only generates a 50 millivolt drop across it.
Oh, so it barely slows it down at all.
Right. It's a tiny voltage, but the microcontroller's analog-to-digital converter is sensitive enough to read that drop and instantly calculate the exact current.
But the moment you're trying to measure millivolts in a high-power environment, I mean, the physical layout must become a nightmare. I remember reading about Kelvin connections in the layout guides.
Oh, Kelvin connections are crucial here.
Because if your resistance is that low, the copper traces connecting the brain to the resistor probably have more resistance than the shunt itself.
They absolutely do. If you just tap into the main power traces carrying those 50 amps, the resistance of the copper trace will completely skew your voltage reading. It'll be useless.
So how does a Kelvin connection fix that?
It uses a 4-wire measurement. It basically runs 2 completely separate microscopic sense traces directly to the innermost pads of the shunt resistor.
Just for measuring.
Exactly. These sense traces carry almost zero current, which means there's no voltage drop along them at all. They serve purely to transmit that exact potential difference directly back to the silicon brain.
So it's separating the heavy lifting power path from the delicate measurement path, even though they physically connect to the exact same component.
Precisely.
That's brilliant. And the Mechatronics Handbook actually takes this concept of resistance as a sensor even further with strain gauges.
Yes, using mechanical deformation.
Right. So you bond this zigzag pattern of metallic foil to a robotic joint. And when the joint flexes, the foil stretches, its crystalline structure elongates, and its resistance increases by this tiny microscopic fraction.
And the challenge there is that word microscopic. I mean, the change in resistance when a robotic finger touches an egg might be a fraction of an ohm.
You can't just hook a multimeter up to that.
No, especially not with the thermal noise present in a robot. I mean, just the temperature of the room changing will alter the resistance of the foil way more than the mechanical strain ever will.
So how do you isolate the mechanical touch from just like the ambient temperature drifting?
You build a Wheatstone bridge.
Okay, what is that?
It's this clever arrangement where you put 4 resistors in a diamond configuration, balancing the voltages across 2 parallel legs.
Okay.
So if you place a dummy strain gauge on a rigid part of the robot, a part that experiences the exact same ambient temperature but doesn't flex at all, and you place the active strain gauge on the actual flexing joint.
Oh, I see where this is going.
Right. The temperature fluctuations affect both sides of the bridge equally, so the thermal drift just cancels itself out completely.
It's an elegant physical subtraction algorithm, built directly into the analog hardware. No code required.
None at all. The only thing that unbalances the bridge and produces a voltage is the actual physical deformation of the metal.
That is so cool. Okay, so moving from the friction of resistors to the energy storage of capacitors. Again, the textbook definition is pretty simple. 2 conductive plates separated by an insulator storing energy in an electrostatic field.
Right, the basic stuff.
But the STM32 high-speed layout guidelines, they dedicate an enormous amount of space to decoupling capacitors. Why is a high-end microprocessor so incredibly fragile that it needs an entire network of capacitors just to stay conscious?
It really comes down to the speed of modern silicon. I mean, an STM32 microcontroller might be running at 400 megahertz.
That's fast.
Extremely fast. When a block of logic gates inside that chip, switches states to process, a piece of math, it requires an instantaneous gulp of electrical current. We're talking about a transition happening in picoseconds.
And I'm guessing the main power supply, like the battery or the regulator, is just too far away to deliver that?
It's not just physical distance. It's the parasitic inductance of the copper traces connecting the power supply to the chip.
Wait, a straight copper trace has inductance?
Any piece of conductive metal has inherent inductance. It resists rapid changes in current flow, period. So when the chip demands a massive spike of current in a picosecond, the copper trace simply refuses to let that current accelerate fast enough.
It acts like a choke.
Exactly. The trace chokes the current delivery, the voltage at the chip's power pins instantly plummets, and the chip's internal logic just collapses. The processor resets.
Just because the wire couldn't deliver it fast enough.
Right. So to prevent this, you place a decoupling capacitor mere millimeters from the chip's power pin. It acts as a local reservoir of charge.
Like a little water tower right next to the house.
Yes. Because it's so physically close, there is virtually zero trace inductance. When the chip demands that high-frequency gulp, the capacitor provides it instantly, holding the voltage steady until the slower main power supply can catch up.
But the STM32 manual doesn't just say, put a capacitor there. It mandates an entire array of them. Like you might see a 10 microfarad capacitor sitting next to a 100 nanofarad one, sitting next to a 1 nanofarad one. Why use a bunch of different sizes instead of just one giant capacitor?
Because every physical capacitor has an alter ego. A capacitor is not a pure capacitance in reality.
What do you mean?
It has equivalent series resistance, or ESR, from the metallic leads and plates, and more importantly, it has equivalent series inductance, or ESL, from its physical geometry.
Oh, so the capacitor itself has the exact same parasitic inductance problem we are trying to solve in the trace.
Yes,
Yeah.
exactly. A large bulk capacitor, like an electrolytic one, has higher capacitance, so it holds a lot of charge. But its larger physical size means it has higher ESL.
It's too slow.
Right, it cannot react fast enough to the highest frequency current demands. Meanwhile, a tiny, microscopic 1 nanofarad ceramic capacitor holds very little total charge, but its ESL is almost zero.
So it can dump its energy instantaneously. So the array acts like a tiered rapid response team. Like the 1 nanofarad capacitor covers the picosecond demand, stopping the immediate crash. But then it runs out of juice, a few nanoseconds later.
And by that time, the slightly larger 100 nanofarad capacitor's inductance has been overcome, so it takes over the load.
And then the massive 10 microfarad bulk capacitor kicks in to sustain it until the actual power supply finally ramps up.
It's a beautifully orchestrated handover of charge across different frequency domains, and it's all dictated by the physical dimensions of the components.
That is mind-blowing.
And if you route the traces wrong, say you place the capacitor on the back of the board and connect it with a via, which is a plated hole through the fiberglass.
No.
Yeah, that tiny cylinder of metal adds enough inductance to completely ruin the handover.
Yeah.
And your robot's brain crashes.
Wow. Which perfectly sets up the third passive component, the inductor. We've been talking about parasitic inductance as the enemy, right? The thing choking our high-speed power. But when we look at the TI motor control schematics, we see massive, deliberate inductors being used in power regulation.
Oh, yeah. If capacitors store energy in an electrostatic field, inductors store it in a magnetic field. They act like the massive inertia of an electromagnetic flywheel.
So they violently oppose sudden changes in current.
Exactly. If you try to push a spike of current through an inductor, it absorbs that energy to build its magnetic field, smoothing the spike out. If the current suddenly drops, the magnetic field collapses, inducing a current to keep the flow going.
They are the ultimate low-pass filter. I know the documents highlight their use in switching regulators, basically taking the chaotic high-frequency chopped power from a transistor and hammering it into a smooth, steady, direct current.
Right.
But there's a catastrophic failure mode mentioned in the literature regarding inductors: core saturation. What happens when the flywheel spins too fast?
Well, to pack a lot of inductance into a small physical footprint, we wrap the copper coil around a core of ferromagnetic material like iron or ferrite.
Okay.
This core concentrates and amplifies the magnetic flux. But there is a hard physical limit to how much magnetic flux a piece of ferrite can hold. Once all the magnetic domains within that material are perfectly aligned, the core is saturated.
This is physically full. It literally cannot accept any more magnetic energy.
And the moment that happens, the component stops acting like an inductor. Instantly. It just becomes a piece of coiled wire with virtually zero resistance.
Oh, geez. So if this happens in a switching power supply?
The current violently spikes, and the massive thermal overload will instantly blow the controlling transistors to pieces. Boom.
Just a total meltdown.
Yeah. So designing around the saturation current limit, factoring in the ambient temperature of the robot's environment, is a massive part of mechatronic power design.
Okay, so we have our passives reacting to the physics of the environment. But to actually make a robot move, we have to transition to the active components. The semiconductors, the things that exert logic and direction over all this raw power.
Diodes and transistors.
Let's look at the diode first. Fundamentally, it's a p-n junction. You dope silicon with impurities so one side has an excess of electrons and the other has a deficit or holes. It creates a one-way electrical check valve.
Right. The physics of that junction dictates that current can easily flow from the anode to the cathode. We call that forward bias. But if you try to push current backwards, the charge carriers are pulled away from the junction, creating this massive depletion region that blocks the flow.
Okay, so we talked earlier about inductors violently opposing changes in current. The TI motor drives pair these two components together in what they call a flyback diode.
A lifesaver in robotics.
Right, because if a robot is driving a heavy motor, which is basically a giant inductor, and the controller suddenly commands the motor to stop by opening a switch, what happens to that massive magnetic field?
The field collapses instantly. The inductor attempts to force current through the open switch to maintain the flow.
But the switch is open, so the resistance is near infinite.
Exactly. And according to Ohm's law, a massive change in current against near infinite resistance results in a catastrophic voltage spike. We're talking thousands of volts generated in a microsecond.
And that spike will seek the path of least resistance, which usually means harnessing directly through the silicon of your expensive control processor, completely destroying it.
To mitigate this, we place a diode in parallel with the motor coil, but we place it in reverse bias relative to the main power supply.
So normally it doesn't do anything.
Right. Under normal operation, the diode acts like a brick wall. The power flows straight into the motor. But when the switch is thrown and that massive reverse voltage spike occurs, it hits the diode from the opposite direction.
Ooh, the diode is suddenly forward biased.
Yes. The check valve flies open. It gives that angry, trapped inductive energy a safe, low-resistance loop to circulate through, bleeding off the energy as heat within the motor coil itself, instead of frying your logic board.
That is so smart. But the manuals emphasize that you can't just use any cheap diode for this. They specify fast recovery diodes or Schottky diodes. Why does this speed of the one-way street matter?
Because of a phenomenon called reverse recovery time. When a standard silicon diode is forward biased, the PN junction is flooded with charge carriers. If the voltage suddenly reverses, the diode doesn't close instantly.
Wait, really?
Yeah, it takes a finite amount of time, maybe a few hundred nanoseconds, to sweep all those charge carriers out of the junction and reestablish the barrier.
So for a fraction of a microsecond, the diode actually allows current to flow backward.
Exactly. And in a high-frequency switching motor drive where you might be pulsing the motor 20,000 times a second, those microscopic moments of reverse leakage create massive thermal losses and tons of switching noise.
So how does a Schottky diode fix that?
It substitutes the P-type silicon with a metal contact. This removes the minority charge carriers entirely, meaning there is virtually zero reverse recovery time. It snaps shut instantaneously.
That level of material science optimization is just incredible. But diodes are still passive in their logic, right? They just react to the voltage polarity. To get true control, we need a transistor, the foundational building block of all logic and power routing.
The big guns.
Yeah. And the texts dive deep into the transition from bipolar junction transistors, or BJTs, to metal oxide semiconductor field effect transistors, MOSFETs.
Right. So a BJT is a current-controlled device. You feed a small current into the base terminal, and it allows a proportional larger current to flow from the collector to the emitter.
Like a faucet.
Exactly. It's fantastic for analog amplification, but for robotic power systems, we don't want amplification. We want a hard switch, on or off. And for that, we use MOSFETs.
Because the architecture of a MOSFET is entirely different. You have the source and the drain, where the heavy current flows. But the control terminal, the gate, is completely insulated from the rest of the silicon by this incredibly thin layer of silicon dioxide. Basically glass.
Yes. And because of that glass insulator, no current physically flows into the gate. A MOSFET is controlled entirely by voltage electrostatic pressure.
Okay.
When you apply a voltage to the gate, the electric field reaches through the glass and pulls charge carriers out of the underlying silicon, forming a conductive channel between the source and the drain.
The texts rave about MOSFETs because they have near infinite input impedance. Since no continuous current flows into the gate, they're wildly efficient. But, and here's where I need to push back.
Sure.
If the gate is insulated by a dielectric, and it has a conductive plate on top and conductive silicon underneath,
Yeah.
isn't that just a capacitor?
Ah, that is the crucial insight, yes. The gate of a MOSFET is literally a capacitor. And while it doesn't draw a continuous direct current, you still have to charge and discharge that gate capacitance every single time you want to turn the switch on or off.
So if you were trying to switch a heavy motor MOSFET at like 50 kilohertz, the microcontroller can't just apply a gentle voltage.
No, not at all.
It has to act like a fire hose, blasting a massive spike of current into the gate to charge that capacitor in nanoseconds. Otherwise, the MOSFET spends too much time partially open, acting like a resistor, and melts itself.
That is exactly why you need dedicated gate driver ICs. A fragile little microcontroller pin can't source the 2 or 3 amps required to instantly charge a heavy MOSFET gate.
It would fry.
Instantly. So the gate driver sits between the brain and the brawn. It translates the delicate logic signal into a brutal, high-current punch to snap the gate open and closed.
And the complexity really multiplies when we arrange these MOSFETs to actually control a motor's direction, the H-bridge topology.
Oh, the classic H-bridge.
Right. 4 MOSFETs arranged in an H pattern with the motor in the crossbar. By turning on diagonal pairs, we can route the direct current forward or backward through the motor coil.
It's an ingenious piece of solid-state routing, but it introduces one of the most terrifying failure modes in power electronics. Shoot through.
Okay, let's trace that. Let's say the top left and bottom right MOSFETs are on. The motor spins forward. Now we want to instantly reverse direction. The microcontroller tells the top left to turn off and the bottom left to turn on.
But remember the gate capacitance we just discussed. A MOSFET does not turn off instantly.
Right.
It takes a few dozen nanoseconds for that gate capacitor to discharge and the channel to actually close. If the microcontroller tells the bottom MOSFET to turn on at the exact same instant, it tells the top MOSFET to turn off.
There will be a brief window where both switches on that side of the H-bridge are partially open.
Yes.
Oh, and if the top and bottom switches on the same side are open, the current doesn't go through the motor at all. It shoots straight down from the positive battery rail to the ground rail.
It creates a dead short across your main power supply. Hundreds of amps will flow straight through the silicon in a matter of nanoseconds.
That sounds expensive.
The MOSFETs will literally explode. They blow the tops right off their plastic packaging.
Oh, so how do you prevent that?
The firmware must inject dead time. It commands the top switch to turn off, then deliberately pauses for maybe a microsecond, waiting for the gate to fully discharge before commanding the bottom switch to turn on.
So the software has to explicitly account for the imperfect physics of the hardware.
Always.
Which brings us perfectly to the STM32 and ALLPCD design guidelines. We've mapped out these complex topologies, the decoupling networks, the flyback diodes, the H-bridges, but laying them out on a physical printed circuit board is where the real dark arts of mechatronics begin.
Dark arts is right, because on a software schematic, a line connecting two components is just a perfect conductor. But in reality, on a PCB, that trace of copper is an antenna. It's an inductor. It's a capacitor.
The guidelines are incredibly strict about trace geometry, specifically for high-speed digital signals. I mean, we usually think of electrical current as electrons pushing each other down a wire like marbles in a tube.
Right.
But the advanced texts describe high-speed signals differently. They describe them as electromagnetic waves propagating through the dielectric material surrounding the copper trace.
It's a massive shift in thinking. As the switching frequency of the processor increases into the hundreds of megahertz, the wavelength of the electrical signal approaches the physical length of the copper traces on the board.
Okay.
When that happens, you can no longer treat the board as a simple circuit. You have to treat it as a transmission line.
The text mentions impedance matching a lot. Like, if you were routing a memory bus on the STM32, you have to guarantee that the trace has exactly 50 ohms of characteristic impedance along its entire length. But this isn't resistance you can measure with a standard multimeter, right? What dictates characteristic impedance?
It is entirely dictated by the physical geometry. Yeah. The width of the copper trace, the thickness of the copper, the distance between the trace and the ground plane beneath it, and the dielectric constant of the FR4 fiberglass separating them.
So if any of those physical dimensions vary, even by a fraction of a millimeter, the impedance changes.
Yes.
And what happens if the high-speed wave hits a section of trace where the impedance suddenly changes? Say the trace gets slightly wider to go around a mounting hole.
It acts exactly like an acoustic wave hitting a desk wall. A portion of the wave's energy propagates forward, but a portion of it reflects backward toward the source.
Oh, wow.
And this reflected wave collides with the oncoming signals, creating constructive and destructive interference. The pristine square-wave digital pulses become distorted. They start ringing and overshooting.
And then the microcontroller reading that signal might interpret a 1 as a 0, and your system crashes. This is why there's that legendary debate about right-angle traces in PCB layout, isn't it? Historically, designers avoided making sharp 90-degree turns with copper traces, opting for two 45-degree bends instead. The old theory was that the electrons would literally crash into the sharp corner and reflect back.
Which is a fundamental misunderstanding of the physics. But the practice of avoiding 90-degree corners remains valid for completely different reasons.
Like what?
At a sharp 90-degree corner, the physical width of the trace effectively increases across the diagonal of the bend.
Oh, right. Geometry.
Yeah, that sudden change in geometry causes a momentary drop in the characteristic impedance, which does cause a slight signal reflection.
Though, to be fair, the advanced signal integrity experts note that you have to be operating in the multi-gigahertz range like radar or high-speed data interconnects before the reflection from a single 90-degree corner actually causes a catastrophic bit error.
True. But the other reason we avoid right angles is manufacturing reliability.
Oh, yeah, the acid etching.
Exactly. During the PCB etching process, where acid washes away the unwanted copper, the acid can pool in the inner 90-degree corner. It over-etches the trace and can cause a microscopic fracture.
So we use smooth curves and 45-degree chamfers to respect both the fluid dynamics of the manufacturing acid and the electromagnetic wave propagation of the signal.
Exactly. It's multidisciplinary.
The layout guidelines also heavily emphasize the concept of the return path. We always focus on the trace carrying the signal from the chip to the sensor, but the circuit has to complete, right?
Yeah.
That current has to find its way back to the source through the ground plane.
And this is where human intuition really fails us. If you ask a student how the return current flows through a solid copper ground plane, they'll usually say it takes the path of least resistance, a straight line from the sensor back to the source.
And for slow DC signals, they are correct, right?
They are, but for high-speed digital signals, the rules change dramatically.
How so?
High-frequency alternating current does not take the path of least resistance, it takes the path of least inductance.
Wait, least inductance?
Yes. And the path of least inductance is directly underneath the signal trace itself. The high-speed return crowds directly below the outbound trace, mirroring its exact path on the layer below to minimize the loop area of the electromagnetic field.
That's fascinating. So if you route a high-speed trace over a solid ground plane, the return current tracks right beneath it. But what if you have a split in your ground plane? What if you routed another trace on the ground layer that cuts across that path?
That is a critical layout error. The high-speed return current reaches that gap in the copper and is forced to divert. It has to loop all the way around the obstacle to find its way back.
Which creates a massive detour.
And that detour significantly increases the loop area of the circuit.
And a large loop of high-frequency current is essentially the definition of loop antenna, isn't it?
Exactly. It will radiate massive amounts of electromagnetic interference, or EMI, completely corrupting the sensitive analog sensors nearby. You have physically designed a radio transmitter into your robot by accidentally slicing your ground plane.
Man, that's brutal. And the physical board material itself isn't immune to these environmental challenges either. The ALLPCB resource outlines different substrate materials. FR4 is the standard. It's woven fiberglass impregnated with epoxy resin. But its dielectric properties aren't static.
Not at all. FR4 is highly sensitive to temperature. The document discusses the glass transition temperature, or TG. This is the temperature at which the rigid epoxy matrix begins to break down and transition into a soft, rubbery state.
Which sounds bad.
Very bad. Standard FR4 has a T around 130 degrees Celsius.
Which seems high, until you realize a heavy motor driver IC on a robotic joint can easily hit 100 degrees. And if the robot is operating in an industrial environment or under the hood of a car, the ambient temperature pushes the board right to its melting point.
And as the temperature approaches the TIG, the material doesn't just physically warp, its dielectric constant shifts wildly.
Meaning the carefully calculated characteristic impedance of your high-speed traces changes on the fly.
Exactly. The board literally falls out of tune as it heats up. So for these high-temperature environments, you have to spec high-TG FR4 or even polyimide materials.
And if you are driving insane amounts of power like high-intensity LiDAR lasers or massive traction motors, even high-TG fiberglass isn't enough, right? Because fiberglass is a thermal insulator. It traps the heat against the components.
Oh, yeah. In those scenarios, the layout guides move you to metal core PCBs.
Metal core.
Yeah, the core of the board is a thick slab of aluminum or copper. A microscopic, highly engineered dielectric layer is bonded to the metal, and the copper traces sit right on top of that.
That sounds incredibly hard to manufacture.
It is. The dielectric has to be thick enough to withstand thousands of volts of electrical potential without shorting to the metal core, but thin enough to allow thermal energy to conduct through it at an incredible rate.
So the entire circuit board basically becomes a massive active heat sink. It's astonishing how every single design choice is a negotiated surrender with the laws of physics. Which brings us to our final exploration. System integration. We've perfected our passives, balanced our active bridges, and routed our impedance-matched PCBs. Now we have to interface with the chaotic physical world.
The real test.
The U.S. LiDAR application notes provide this fascinating case study on sensor fusion, specifically integrating LiDAR with an IMU, an inertial measurement unit.
Right. LiDAR is the ultimate spatial mapping tool. It fires rapid pulses of laser light and measures the exact time of flight for the reflection to return, building a millimeter-accurate 3D point cloud of the environment.
But as the application notes reveal, a LiDAR sensor operating in isolation is fundamentally compromised by its own physical mounting.
It's a major paradox.
Yeah. The manual poses a scenario that feels completely counterintuitive. You mount a heavy, expensive LiDAR unit on a rigid tripod at a construction site to map the topography. The LiDAR isn't moving. Yet the documentation highly recommends integrating an IMU alongside it. Why does a stationary sensor need an accelerometer to track movement?
Because in the context of millimeter-accurate laser optics, the concept of stationary is a myth.
A myth?
Yeah. The tripod is resting on soil. A heavy excavator driving 100 yards away sends acoustic shock waves through the ground. The wind buffets the chassis of the sensor. These forces create microvibrations.
Okay, but how much can a microvibration really affect it?
Think about the geometry. If the laser beam shifts its angle by just 1/100th of a degree at the source due to a tiny vibration, by the time that beam travels 200 meters, the physical dot hits the target several inches off its true mark.
Oh, wow.
And it's doing this millions of times a second. The entire 3D point cloud becomes blurred and warped by the ambient noise of the environment.
That is where the IMU comes in. It contains microscopic silicon structures, MEMS technology, that measure the exact angular rate and acceleration of the LiDAR chassis in real time.
Right. The processing board takes the massive stream of LiDAR distance data and mathematically correlates it with the high-frequency vibration data from the IMU.
So it dynamically calculates the microscopic tilt of the sensor at the exact microsecond the laser fired and applies a geometric correction to the point cloud.
It's algorithmic image stabilization for lasers.
But the manual presents a brutal decision matrix for the hardware engineer here. You have to choose between a tiny, cheap MEMS IMU integrated directly onto the LiDAR circuit board or an external, highly expensive tactical-grade IMU.
And this isn't a minor cost difference either. An integrated MEMS IMU might cost $50. A tactical-grade external IMU, potentially using fiber optic gyroscopes, that can easily cost over $10,000.
I have to challenge this logic, though. The manual suggests that if the robotic platform is moving faster than walking speed, or if it requires simultaneous localization and mapping SLAM, you have to use the $10,000 external IMU.
That's the recommendation.
But we see startups building autonomous delivery robots and drones that cost a fraction of that total. How are they surviving without tactical-grade IMUs? Are they just accepting massive error rates?
Not exactly. They're relying heavily on software estimation to compensate for the hardware's physical limitations. Specifically, a flaw inherent to all MEMS IMUs, bias instability and drift.
Okay, let's unpack that drift mechanism.
Yeah.
How does a silicon sensor just forget where it is?
Well, a MEMS gyroscope measures rotation by vibrating a microscopic tuning fork structure etched into the silicon. When the chip rotates, the Coriolis effect exerts a physical force on that vibrating structure.
Okay.
This alters its capacitance, which we measure, but the mechanical properties of that silicon structure change slightly with temperature fluctuations, mechanical stress from the PCB warping, and inherent electronic noise.
So even if the robot is sitting perfectly still, the IMU might report a microscopic rotation of, say, 0.001 degrees per second.
Yes. And because you have to integrate that rate over time to calculate the robot's actual heading, that tiny error accumulates constantly. It's called random walk.
So after 10 minutes of driving in a straight line, a cheap MEMS IMU might be convinced the robot has slowly veered 30 degrees to the left. So to answer my own question about the startups, they use Kalman filters. They take the drifting, noisy data from the cheap IMU, and they constantly cross-reference it with the LiDAR data and wheel odometry.
That's the secret sauce.
Right. If the IMU says the robot is turning, but the LiDAR sees that the walls of the hallway are still perfectly parallel, the software dynamically recalculates the IMU's bias error and nullifies it.
Exactly. They are substituting expensive, flawless hardware with incredibly complex software sensor fusion.
But there's a limit, right?
Oh, absolutely. The manual states that for safety-critical applications like autonomous vehicles operating at highway speeds, you cannot rely entirely on software filters to save you.
Because it's too slow.
It's just too unpredictable. High dynamic forces, swerving, braking, hitting potholes, they can induce massive nonlinear errors in cheap MEMS structures that a Kalman filter simply can't predict fast enough.
And if the software guesses wrong for a fraction of a second at 70 miles an hour, the consequences are fatal.
Therefore, the physics dictates the budget. For those applications, you must use the tactical-grade external IMU, where the drift is measured in fractions of a degree per hour, not per minute.
It all circles back to the core philosophy of mechatronic engineering. I mean, you can optimize the shunt resistors to read millivolts of torque. You can perfectly impedance match your high-tech FR4 traces. And you can tune your MOSFET dead time to the nanosecond.
But ultimately, you are building a bridge between pristine logic and a chaotic, vibrating, thermally hostile universe.
The hardware is the interface.
Yeah.
And understanding the parasitic physics of every single component, knowing that the resistor is an inductor, the trace is a capacitor, and the sensor's fundamentally drifting is what separates a theoretical design from a robot that actually functions in reality.
Well said. But as we look to the future, even these boundaries are starting to blur.
How so?
The advanced mechatronic literature touches on micro and nanotechnology. As we push towards nanoscale electromechanical systems, the clear lines we drew today between a resistor, a capacitor, and a processor, they're vanishing.
Wait, really?
Yeah. Imagine a future where a single microscopic structure isn't just a physical support for a chip, but simultaneously acts as the resistor, the capacitor, the sensor, and the processor all at once.
So the material itself is the robot.
Exactly.
Mhm.
When physics and code become the exact same thing, how will we even define what a machine is?
That is a wildly provocative thought to end on. This has been a massive journey. We stripped away the sci-fi magic and found a reality that is arguably even more fascinating. The intricate choreography of charge carriers, the structural limits of fiberglass, and the mathematical alchemy of sensor fusion.
It really changes how you look at the tech around you.
It does. The next time you see a machine navigate the world, don't just see the code. See the physical struggle playing out across millions of microscopic gates. Thank you for joining us on this exploration of the invisible forces that animate our world. This has been The Deep Dive.